Hello and welcome to this buildingSMART room session as part of the buildingSMART International Standards Summit. Thank you for joining us today. My name is John Proctor and I will be your moderator. This is the technical room session number 3. We will be hearing, as shown on the screen, from Greg Vazzana, Diaz, and Jago from joining this session. If you have any questions or comments, please add them to the pop-in chat, and we will deal with them at the end of the session. Before I hand over to Greg, I'd like to remind you this is a hybrid session. For online attendees, your microphones will remain muted for the duration of the session. And if you wish to ask a question, as I said, please use the chat box in the control panel. In the room, please enjoy the session, and if we can keep background noise to a minimum, that will help with the microphones. I'd also like to bring to your attention the information that is on the screen now. buildingSMART is committed to ensuring that participation in the development of standards is unrestricted, and the process for their adoption is transparent, and that standards that are developed do not favour any particular provider, but are open, non-binding and accessible to all. Please take note of our antitrust code of conduct. Okay, we're going to start. So we could start with Devon. Devon, do you want to go first for the presentation today?
Sure. Yeah, I can. Hi, everyone. I know it says Leif down, and if Leif's in the room, good to see you, Leif. So Leif was going to present on all of this section, but I was asked to speak specifically on when we're talking about kind of ECS in the wild, talking a little bit about. Do you want me to still go, or do you want Greg to take over?
We are going to move to Devon because we lost you, Greg. How are you now?
Okay. That's fine.
So I was asked to speak a little bit about kind of ECS in the wild, and specifically how Trimble has implemented it in its property set service. So I am not Leif. I'm a enterprise data architect at Trimble working on the core platform. So I'll start to share my screen. Share screen. So forgive me, I haven't been part of some of the earlier sessions, so I don't know what context has been set about kind of the entity component system discussion, but this spun up. I think I had a conversation internally with a few folks. I talked to Greg Schleichner a bit about this, and there's this really interesting pattern that's kind of emerging both within the standards communities and within the different vendors about the use of this entity component system pattern. So just kind of one quick slide to set context, or at least how I think about these kind of entity component models, is what's interesting about them compared to a lot of traditional object-oriented modeling is just how compositional they are. And they're really made up, I like to think of it like a incidence matrix where you have two different major types of elements. You have entities, which are primarily identifiers. So that might be a GUID, that might be a URI. You just, within some address space, you have a way to uniquely identify some asset or something that you want to track. And in this particular diagram, those are the kind of rows that you see there. And then orthogonal to those are a collection of components. And I normally think about these as a set of kind of functionally related property definitions. So you might have a component that represents all of the performance requirements for a particular asset, which could apply as much to doors as it does to I-beams. You could have a component that represents its location in a Cartesian space, or maybe a set of properties of a component representing its representation. And the key point about an entity component model is really how these two different pieces, the entity, which is the identifier, and the components, which are like the standard definitions, interact with each other. You can see that any entity, if you look across the row, like an I-beam, can have multiple components as part of it. And a component type, like a location, can belong to multiple entities. So by basically filling in this matrix in different ways, you build up this compositional model where you can have a bunch of information that all follows similar rules applied to different entities. Something is not just a door anymore, but can have different points of view. So it's a bit of a departure from the traditional inheritance mechanisms people think about, But increasingly, we've been finding, and I think the industry as a whole is finding, that this compositional model is helpful for the kinds of work we need to do. So when we were talking about ECS and just kind of observing patterns that are happening in the wild, it was like, hey, we've got one of these things at least one of these things at Trimble, and I thought it was a good example to show how this is being used in practice today. So we have this thing called the Trimble set property set service, and the name property set itself in the service's name actually is derived from IFC, and it really is at its core an entity component oriented microservice. So this is something that we offer as part of Trimble Connect, which is one of our cloud-based kind of common data environment. It's deeply integrated with Connect's 3D workspace and kind of workbench experience. And under the hood, it provides a standard HTTP API. We've got real-time eventing support. It does version history on all the property sets and their definitions. It does internationalization, fine-grained permissions, like all the kinds of things you'd want to really have in a collaborative entity component system. And interestingly, for this particular service, is that it actually uses a type of semantic data typing that is derived from IFC. So it's actually fairly close to and influenced by the open standard itself. And this thing has been in production in multiple regions, I think, since about early 2018. I've used it to write a lot of client integrations with good success, and it's a small and lightweight service that's part of a bigger ecosystem. So that's kind of the property set service in a nutshell, but it's worth seeing how the interactions we have with it and customers do work in the normal Connect experience. But just before we get to that, I kind of want to lay out just the key foundations of how the PSET service works. So at the top level, you have the idea of a library, and a library is basically some container that holds one or more what we call PSET definitions. So these are collections of properties and all of their constraints. So a single library will own one or more PSET definitions, and our PSET definitions map pretty directly to the overall concept of a component. And then those PSET definitions, which defines, these are the 5 attributes, these are their constraints, these are their semantic types. You can take any one of those things and you can instantiate it and make an individual, what we call a PSET. And that's a particular instance of that definition that has the data values that you may care about for a particular use case. Once you've created that instance, then you can go ahead and link it to what we in the system are called links, but these are ultimately just the entities that we were talking about on the earlier slide. So this connection, by being able to define a component and basically say what its makeup and its constraints are, you can instantiate it and then create an individual instance of that definition, and then link it to any entity that can be identified by identifier, is the core of the system. And what's powerful about it is that link all the way on the right-hand side of the screen can be anything. It could be a URI, it could reference a QR code, it could be an IFC GUID. The system really doesn't care what you use as your identifier. And these last three, if you cut out the library part of the page, the PSET definition, PSETs, and links are equivalent to that incidence matrix I showed on the first slide. So really at its core, the Trimble property set service is an entity component system. If we were to go and look, so not at the individual API layer, but within one of our, kind of front end experiences, this is what you might see. So if you were to log into Trimble Connect today and you go to the left-hand panel, you could first take a look at some of the property set libraries. So you can see here in this particular project, I've made a number of libraries just to partition out different property set definitions into functional categories, and I can create new ones. Once I'm within a particular library, I can go ahead and create a single property set definition. So you can see one here for commissioning, and then it has multiple properties that are inside of it. And I can create a bunch of new properties as I go, I can edit them. And if you look on kind of the right-hand side there, you can see not only can I give it a name and a description, but I can actually do some semantic tagging on its type, not just that it's a string or text, but actually some, is this a length or an area measure or something like that, as well as kind of enums and drop downs. So we provide this front end to try to allow more stakeholders in the process to be able to actually create these PSETs or components and begin to use them in their work. And so once you've kind of gone through this editing process for a particular PSET, you've really done the work to be able to start enriching any model you have. So here we are switching over to this is a view into the kind of Connect 3D workspace. And here's the IFC duplex model that everybody knows and loves. And here the workflow is really pretty simple in that any entity, so this is in this case, you know, any particular wall or slab that you might have in the model, I can select any number of them and then attach to them and say this collection of entities should conform to these pset libraries. It should be able to have this type of data attached to it. So once you've attached a library data to any number of entities, you can actually start to add physical pset data to it. So you imagine now I've selected an entity. I've gone ahead and added the libraries that are relevant to it. Now I can kind of bring up a property set window in the right-hand panel. I can choose the commissioning property set that I had just loaded up on the earlier screen and go ahead and edit its individual value. And when I do that, what I've done is in the background taken the GUID that represents this slab and annotated it with the pset that is actually stored in the pset service. So I have enriched the model with component information that's stored outside of the model itself, but can still be enriched and linked in the 3D space because I know what the GUID or identifier for this asset is. And that's, of course, a standard. That's what you get out of the box if you were to look at Connect as a kind of front-end, you know, cloud-based user experience. But under the hood is all of the kind of HTTP API itself, where there's actually much more flexibility in the kinds of things you can do. And as I've written custom systems on top of this, there's a lot further you could go to build custom experiences. So not only do you have all of the usual kind of CRUD operations, but the fine-grained access control allows you to actually change the visibility of what kind of stakeholder can see which kinds of components. So you can say things like, you know, only people within this domain, or at this domain address, or with this particular email, should be able to see components of this type. And what's really interesting about that is that you can go ahead and begin to present different views of the same entity, the same slab, depending upon who you are and what authorization you have. This underneath the hood also provides, as I think I alluded to in the beginning, real-time change notification. And what's been interesting about this is you can start to really build up interesting collaborative workflows where as people begin to enrich and annotate assets with this metadata, you can trigger actions to occur as soon as a particular property or value has been set. So I found a good effect with that as well. And kind of backing up a level, one of the consequences of not just this model in the Trimble property set service, but I think for most of us working in these entity component systems is they start to change the way you think about asset enrichment and information exchange. Is that a big thing about having these services out there that can use an entity component model means that asset data, all the metadata, you know, in these components is no longer bound to a particular file or even a specific model. Really, the goal is that anyone, whether they know how to use an authoring tool or not, should be able to contribute the relevant knowledge they have of this asset to it, as long as they know how to find its name and they're authorized to do it. That's why these asset identifiers are really important. We've also found that having a system that not only supports this data model, but also supports the fine-grained permissions on top of it, means that you can have different stakeholders seeing different views or representations of the same thing. And especially in complex projects with different levels of trust and with many different phases, this fine-grained permissioning has turned out to be a really helpful layer on top of the base data model. And the final note that I think I'm guessing we're going to hear in some of the other things is it also begins to put a stronger emphasis on the need for stable asset identifiers. One of the keys to this system, as we saw in the beginning, is that you really need to be able to give something a canonical name so that you can kind of hitch or attach information to it and then reference it again later. So what's important is that these kind of, whether it's an IFC GUID or some kind of persistent identifier needs to be on these assets so that changes across time and stakeholders can be mapped consistently. So those are, I think, the three consequences I've learned both in using the system and in kind of building things on top of it. And I'd be curious to cross-reference with the other speakers if they've seen the same thing. So that's just, this kind of covers, this is one example of what's out in the wild. It's an instance of a general pattern, and one we're increasingly finding good, and our customers are finding good value for. If you are curious to learn more either about Connect or the PSET API itself, there are two links to take a look at. And I think that's kind of where I wanted to just give a single case study. So I'll stop sharing and see if there are any questions.
Yeah, that's great, Devon. Thanks very much for that. Do we have any questions for Devon at this point? Anyone in the room? Yeah, there's some hands up.
We'll have to go to the mic this time.
Could you mind going to the mic and just...
Bring the mic to you. Sorry.
From team. We are investigating at the moment a lot of ID schemes, indeed, like URI-based or GUI-based UID users, etc., etc. Also, we have a GS1 cheating for products, and we extend it to assets and all that stuff. And lately, I came across development by W3C, DIDs, the distributed IDs, where there is no single persistent ID, but anyone can have its own distributed ID, given the right metadata, authorization, etc. Do you have any views on what will be the future best ID approach in this sense?
So just to play back, because I had a little trouble hearing, we were talking about the use of UUIDs and IDs, and that whether there is kind of one canonical ID for everything, or if ultimately we're going to need distributed IDs that get linked together. Is that right?
Yeah, right.
I mean,
central versus distributed IDs. What's the future?
Yes, I mean, my speaking personally, I think it will ultimately be inevitable that we'll end up having networks of these things, but it will be important to represent the relationships or equivalencies between them. So for folks who are kind of into the linked data world, there are, fairly standard ways to do this, but one way or another, being able to have, whether you choose a fully canonical address, which is kind of the degenerate case and is simple but not as scalable, or something where you have them linked. I think the use case for entity components is just as relevant. So I think there's a broader discussion in the next session about where, and I think Leif will talk about this as well, where we should go in the future. But ultimately, I will see we will have multiple identifiers, but how to address that cleanly is something we as a community are going to have to work through. So.
Thank you very much. Okay, I'm moving the mic up here, just 1 second.
Cheers, Greg. Do we have any other questions for Devon before we move on to Greg's presentation? Yeah, one more. Here we go.
I give the question here. As you go to the property set service and you can annotate data within the Drupal Connect world, without actually being a model, concept of a model kind of falls apart. What's the mental model that you present to the users of where that data is being stored? Is it organized in a project? So it's all project data. What's the vocabulary that you're presenting for, since you're not editing a model anymore, you're editing your property sets. How do you think about that?
That's a really good question. In the Connect environment, at least, the primary way most stakeholders interact with the PSET service is through the 3D workspace. So practically, the way, even across models, what you'll be able to see is if the same GUID shows up across multiple models, that data will appear in that layer in that workspace. So it really it becomes the 3D environment and all of the assets that get loaded in, whether they come from one model or 10, it's really the 3D space that becomes the context that represents it. So if I can click on it in a 3D space, I can see information that's presented about it no matter where it came from. I haven't interacted with enough customers who are doing building custom experiences on top of it to know if they have presented it in a different way. But you bring up a really interesting case that once you get this data out of a model file itself, it really does live in this separate repository, and the connection back to it is just through this naming convention. So it's a very abstract way of thinking, and there probably is a whole lot of exploration to do in what an effective user experience would look like, especially as we were start to scale up these entity component models across the industry. So yeah, I think that, yeah.
More theoretically. Okay. And just slightly on that, more specifically, what are the default permissions for a new property set?
I'm sorry, could you, something about permissions, I couldn't hear the first part.
Yeah, when you just create a property set, what's the default access that it's given to?
I believe it is, I believe it relates to, and this knowledge is a little bit old, but I believe it relates to anyone on your particular team, which is tied to a connect concept within the ecosystem. But I'd have to double check that. And all of that, if you may have quickly seen in the screen capture I showed of the HTTP API, all of that is overridable. There's a whole description language for kind of fine-grained IAM authorization within it. But I want to say that's the default. I'd have to check though.
So it's kind of like we're defaulting from a model to team information. Right?
Yeah.
Yeah. Cool. Thanks.
Right. Yep.
Okay, we'll move on to Greg. Did we work everything else?
We did? Yep. Thanks, Devon. We're going to move to you now. Thanks, Greg. We're going to move to yourself, Greg. I'll bring your slides up now, but thank you very much.
Okay. All right, so my name's Greg Vazzana. I'm a distinguished architect with Autodesk, and my current focus is all about AEC design information. And you may hear some similar themes here as we talk about ECS, but I think that's all good stuff. Next slide, please. So, I'm going to step back, and before we dive exactly in on ECS and kind of the aspects of it, and talk about what AEC needs for data transformation. As we evolve, as the data becomes more granular, more important to share, we need to change. I shouldn't say we need to change. I should say certain things should be present to make this the best experience it can be. Next slide, please. So unlocking that data, depends on a few different things. Not only is the pattern of ECS and the architectural work important, but it has to be supported through open ecosystems, open APIs, standard formats, and that sort of thing. The data quality aspect is something that I think is important to keep in mind as we go forward. So by increasing that standardization, we want to make sure that the data is of high quality. Being able to attach data of any kind to anything is powerful, but we also want to make sure it is consistent. This, by making data more high quality, more standard, hopefully we're bridging gaps across project lifecycle, reducing errors, hoping they're making data more reusable, less need to remodel, and that sort of thing. And then all the connected systems surrounding this that help with federation or accessing the data at the right time by the right people, collaboration, and all these things that support frictionless exchange, whether they be services or other capabilities on top of the data is also important. Next slide, please. So flexibility is the standard here, I think. So, we have products that have very rigid schemas that have very strong opinions as to what an entity is. And I think over time, those are ultimately not durable. So the key to evolving the data and leveraging a pattern like ECS is to enable partners to use those simple building blocks that we have. I mean, ECS at its heart is relatively simple. So in producing or creating the right level of standardization. So having ways to extend, create schemas, discover them all through open means and open frameworks is really going to let this data evolve and meet the needs of the applications and customers. Next slide, please. And just quickly on data granularity, the data granularity is good and it's helpful to get to a low level of detail or a high level of detail, I guess, in these models. However, we have to keep in mind that what is granular is sometimes workflow specific. It's contextual. So something that has a lot of granular data may just be bloat for some other workflow. So we have to balance that and create a data model that is able to accommodate those kinds of. Okay, next slide, please. So the AC design information model, an entity component system for AEC. Next slide. This is, the key things that I think we need to start with here is embracing that composable nature of ECS, and not being rigid and allowing different taxonomies to coexist, and starting to create well-defined components, not necessarily objects, all based on these common data currencies, what exactly they may be. But creating that level of commonality or using those simple building blocks is what is going to be the basis for AEC using ECS. Next slide, please. So using a simple information model for complex data. So this is how ECS for AEC might look, right? Do you have a design entity, and those design entity have components, and there's a relationship, and with those sort of building blocks, there's a lot you can do to represent complex data. Having some principled, extensible information model gives you that durability that we can last and hopefully stand the test of time. So why don't we go into a design entity on the next slide a little bit. Thank you. So a design entity is this abstract idea of what an AC piece of AC model is. So, starting with classification. So there's, while ECS is extremely flexible and extremely, malleable to the needs, there's probably some level that you need to just understand the intent of what this design entity is. And a design entity can be anything. It's not, it doesn't have to be graphical. It doesn't have to be, it's kind of whatever you decide to classify it as. So having one or more classifications attached to a design entity, technically a component, but I think it deserves to be called out at a higher level. Then you can basically label the design entity and get the intent of it. Then components come into play, which I'll talk about in a minute. And globally unique ID. So this identifier, which is unique across all projects and models or designs, is important for stability and confidence that the data is where you expect it to be. Having that ID mapped to other IDs from other applications is certainly something to think about and how that all works. But I think with ECS, you can achieve that in a few different ways if ECS has a storage mechanism for that. Relationships, another fundamental building block, which I'll talk a little bit about in a minute, and then versioning. So versioning is really critical in an information model where multiple products may be accessing and reading or writing the data. And versioning at a design entity level, not at a wide, broad level, but granular versioning, if you will, I think it helps give that confidence in that idea that a design entity is what you think it is, and you can manipulate it in your application without worrying that it's going to be completely different, let's say, if you pin the version. Next slide. So components, This is where I think we want to have them become well-defined and schema-driven. These components should be serving a singular purpose, so that they're self-contained in that way, that they are doing the thing that they know about and nothing else. And the combination of these gives context to that design entity. One of the keys that I touched on before is that as these things, as we create components, having them be schema-driven and discoverable and useful is important. So I wouldn't expect there to necessarily be a wall component, but there could be a location component. Actually, on the next slide, I can talk a little bit about that. Next slide, please. Thank you. So different components, when they serve a singular purpose, they really need to zero in on that thing. So for example, right, we could have a binary component whose mission in life is to hold on to binary data or reference binary data. That's one really focused component. Classification, I talked about a little bit, but it can go on and on. There could be a 3D representation component, a 2D one, location, property group, property, coordinate system. I mean, it could go on and on, right? So over time, I would expect, hopefully components is possible, but having that ability to create new ones and build up that library of components for use to be combined in different ways that makes sense for the workflows that are being supported. And one quick note about property and property group. I could make an argument that property is real fundamental, as might be one of those common data currencies, and property group is just that collection of those things. That's a case where you might see nested components. There could be nested components, I would imagine, but it really depends on the workflow you're trying to solve and if that makes sense, and if it serves that singular purpose. Next slide, please. The data currencies at the most basic level, these are the things that are the basis of components. That's the data that will be transparent in the sense that it's accessible and open. And hopefully we're leveraging open forms of this data. But the type of data you would see at this level are things like units and maybe some forms of geometry. Something that can be shared and made public so it can be reused. Next slide, please. Relationships, which are another one of the building blocks. Having not prescribing relationships, I think is important. However, products or things writing out these data is going to write out relationships. And, so that we as consumers of the data don't have to establish all the relationships ourselves. But these relationships should have the ability to be decorated to understand what the relationship means. And maybe there are multiple relationships between entities that mean different things. So having data that can be attached to relationships and extended is critical. So you may want to know the difference between a chair being contained in a room versus a door instance and a door being an instance of a door type. So those kinds of things we want to be able to represent and have multiple representations of. Next slide. All right, so data access and management. This is not quite permissioning, although that is very important. This is really meant to talk about, the fact that there's not files, right, in ECS. Everything is related. It's a graph in many ways. So there are certain capabilities in order to make this data consumable that really need to be in place, because presumably the data is going to accumulate over time in these information models, and you don't necessarily want to have to consume all of it for it to be useful to you or your workflow. So having that ability to group data arbitrarily based on certain criteria, whether that be an application that wants you to group data a certain way, or you want to group the data a certain way, having that as a mechanism on top of the information model is going to help bridge that gap away from having files and applications completely decide that for you. Querying, putting this data in there is great, and making it open is great. Getting it out in a way that is not all of it again, having complex queries, doing things like give me a pipes with a diameter greater than 6 inches or something along those lines. Complex queries can be built on top of this data. And then, it also opens the door for other types of queries, maybe text queries, Google type things. All of that is used to serve presenting the data in context for what you are doing. So whether you're using something like Revit to deal with a building and design a building, but your information model also has infrastructure elements in it that was designed in Civil 3D, all that information is there, but perhaps your context is just architectural and building design. So that's the kind of data that would show up even though other is present. Next slide, please. So data exchanges, how does this relate to information models? Slide, please. So data, just some quick principles, supporting multiple ways of data exchange. That we have loads of data that exists today. Information models are great and useful and hopefully will grow over time, but we do need to support different ways of exchanging that information. The exchange mechanisms need to support that data quality and keeping it consistent, so that there's no degradation in the data, and that the control of the access and what data is exchanged is not something that would inherently change the quality of the data. And then allowing different, as I've said before, open standards and formats should be the basis of all of this. But embracing contributions from different applications in order to handle these exchanges or deal with these exchanges, that's also key, so that we can get the data into the right form in the right place and make it useful to the people. So the next slide, please. So there's different ways of exchanging data, right? Loads of products do all sorts of cool things, but they are not going to start out necessarily using data natively or using cloud information models natively, I should say. So, over time, ideally, maybe we're pointing directly to the data in the cloud or some other, networky type thing. And we can use that natively. And then, that you can control how things are exchanged, whether you decide to put access controls on it or whatnot. But that is not necessarily, that's good in a work in progress setting, and applications can provide that access. But we do need other ways to exchange this data in a data information model friendly way. Next slide, please. So data exchanges. These are data exchanges, really a managed reference to a subset of the design information model. It doesn't necessarily need to copy it, but it can directly reference it, and it can reference a controlled subset of data. That's super important. So, while there's loads of information in the data model, it doesn't mean that all of it needs to be exchanged, or should it? So controlling that access through different permission mechanisms across organizational and company boundaries is required for that workflow. It's the most important thing I think here is that it is referencing this data as opposed to actually moving it. Next slide, please. And then there's good old files. Files that's where all the data, most of the data is right now. Over time, currently you could think of them as more of a source of truth, and getting that data into a form that is an information model, it will be critical to leveraging that data in new ways. Once you start to do that, the file kind of changes its role a bit. It changes from being the source of truth to being more of a derived snapshot of this data. So if the data is in the cloud information model or the AC design information model, you could produce a file from that information and make it useful to other applications. But that's useful to get existing data going. I think also having that sort of be part of the system and making it first class is also very useful. I think as it though it is different in the sense that it is a copy of data in a different form. It doesn't replace the original data. Okay, I think that's it for me. There's loads of this is a cool topic. There's lots to discuss. I hope there's questions that we can dive into.
This is Greg. Thanks, Greg. Any questions from the room to get started with? So I'll ask one. From a just from a productization question perspective, you don't have to give sort of detailed answers, but some of this is in the wild and some of it's in development. Can you characterize that a little bit?
Yeah, so there's already exchanges happening with Autodesk. So there's currently different exchanges going on. There's right now, one of the recent ones that was announced was an exchange between Rhino and Revit, and there is ways to do that. So that's one of the first areas that you'll start to see this data show up. Now, and that particular mechanism around exchange is pretty pluggable. So as you connect into it, it becomes useful for everyone that's involved with the exchange. There's a lot of discussion, how to best, it depends on a lot on the products and what their needs are. So the challenge of these information models with the breadth of projects that exist are, it's probably not one data source to rule them all, but having that ability to react to the data that is there, and support a particular product's workflow, that's what we want to teach the products to do. So for instance, if one product writes out let's say a pump to the information model, and it has loads of information, and it writes out 3D geometry, maybe something like Revit would consume just the 3D geometry because the other information is too detailed or not applicable or whatever. It's just so it can place a pump in the building. Things like that are being discussed such that we can make it useful across products and make it seamless.
Okay, thanks for that. Anybody else? Questions, comments? Yeah, just 1 second.
Just one I already had this morning when we were discussing this new approach. In general, when we start modeling, making decomposition trees, velocities in IFC or whatever, we have multiple levels of decomposition. Here it seems like we have entity and then we have components. But how can we then have components of components? Can that be a whole velocity of items that surface each other? It's only one level deep.
Unfortunately, I had a hard time hearing. Can someone repeat the question?
Close to one maybe. I was wondering, can we have this decomposition structure from entities to components? Can it go on? Can components have be decomposed again? Or is it only in general one level deep?
So there was something about decomposing the data into and how.
Sorry, Greg, we have on hold the room.
I'll translate.
Okay.
I think the question, can you hear me?
Yes.
Yeah, I think the question was simply, can we have components composed of components? Is it hard? Is it hard? Yeah,
so yes, there's no limitation as to the ability to do that. I think the overriding principle for components really is about making sure that they are serving that singular purpose and not creating deep hierarchies of components, because then I think you start to stray from the idea of making this composable. You start to say, if you're not careful, you can go down that path of saying, well, this component nests these other components, which nest other components, and bam, you've just created a rigid schema. So as long as you're adhering to that singular focus of the component, I think you're good to go. There's no limitation there.
Yeah, that was great. Thanks, Greg. Thanks very much for your presentation. And I'm just going to remove you from the feed. Please do listen in the background. And we have Diaz.
Well, good afternoon, everyone. My name is Diego Diaz, distinguished engineer at Bentley Systems. I've had the honor to be invited to this event, invitation extended by Bentley buildingSMART, to talk about the architecture that we've been working on at Bentley for over a decade now, in order to solve some of the challenges that we've been discussing at this very room since the morning. Should I just use the arrow? Or use this if you want? Oh, okay. So I assumed we were developing the main challenges this morning, and Greg did a good job this morning to go over the explaining of one of the challenges: multiple owners, data contributors on every project really involving infrastructure data. That really translates. Oops, sorry about that. Greg was mentioning the example of a light fixture involving an architect, a light designer, and an electrical engineer having to collaborate to select the best lighting of a room or of a building. This challenge reflects also on the wide range of file formats supported in the industry, and that presents certainly another challenge to be considered. Each data contributor and file format typically focuses on a single way of conceptualizing a real-world infrastructure asset for a particular purpose. So at Bentley, we call that a modeling perspective. In a way, I've been listening to explanations at these various presentations, and it touches on the concept of representations in IFC. Some examples of what we consider a modeling perspective include 3D physical models, where the focus is certainly achieving an accurate 3D visualization, useful for purposes like clash detection, quantity takeoffs. Some other perspectives, another example is a functional model, where the focus is to understand how the components work together towards providing a particular function in a system. There may be also multiple schematics associated with that. Another example are analytical models, where the focus is more about predicting how the infrastructure asset may behave under certain conditions. Typically, there is some input, a solver or numerical engine, and an output. And this workflow involves the decision-making based on the result set obtained from that numerical engine. Network models, another example of what we refer to as modeling perspectives, where network topology means are applied to understand connectivity and typically do tracing or even linear location along a network. And finally, another example, catalogs and specifications, which cover also drawings and sheets produced through all the various file formats that basically have to be managed in these projects. So I'm just basically going through challenges and setting up the terminology that we use at Bentley. And my last slide about challenges, all of these have to be managed through the life cycle of an infrastructure asset. Simply quite challenging. So let's dive into what we have been doing or working on at Bentley. And it starts with the first notion that I want to introduce here, the digital twin. and we call it at Bentley an iTwin. It is meant to gather and reference different digital representations and data sources about the subject matter of the digital twin. So from reality data, GIS, existing conditions such as terrain, asset performance data, sensor data, and engineering data. When I use the engineering data term to distinguish it from all the rest, engineering data is probably what a typical user would want to store in an IFC file. So just to provide some context. That's what this, I had these slides animated. Unfortunately, the animations were lost in the uploading, but that's okay. This gray circle in the center called the model hub is where we store and manage the engineering data part of an iTwin. And there are two workflows in this architecture in order to bring data into engineering data into that side of the iTwin. One of the workflows is what we call a synchronization workflow, in which we assume that the single source of truth of a particular data set lives outside of the iTwin. Examples, Revit, IFC, or OpenRoads data sets that are synchronized. The data is synchronized into what we call the model hub, and more specifically, iModels. And I'm going to explain what that means in a second. And maintain up to date. So the synchronization is not just one export, but it's basically as data keeps changing outside of the iTwin, we have pieces of technology called iModel connectors, whose job is to detect changes happening and bring them across into the iModel. And lastly, the second workflow to bring data into the iModel hub or into iModels is the authoring workflow, in which the data is created directly in iModels, the iTwin, and therefore the iModel becomes a single source of truth in that case. So as you see, well, we start addressing some of the challenges here by handling external data files, formats in the workflow that we follow. Now I introduced the concept of an iTwin. Let's move down into the concept of an iModel. So what is an iModel? So it is primarily a relational database holding information about an infrastructure asset in terms of a schema architecture that we have developed at Bentley, and we call it BEAS. I'll go through some of its highlights. First of all, it is based on open source technologies. We have a library out there called iTwin.js that enables you read and write access and functionality to an iModel. Second, it captures chain sets. So as changes are happening in the iModel, they are stored in a timeline of chain sets maintained in the iModel hub. The iModel hub is a cloud service that keeps track of all these chain sets and can provide you with an iModel as the incarnation of that data set at any point in its existence. So we have support for data changing over time. It is the format is portable, which means we support cloud-based or portable form factors such as PC, tablet, or the phone. It was built with engineering data in mind, and as I said a minute earlier, it is using a technology for schemas, self-describing schema that we call BEAS. So this is just an intro of what a model is. I guess the highlight here, it is a relational database with a set of BEAS schemas describing its data. So let's dive into BEAS. BEAS stands for Base Infrastructure Schemas. That is a technology that I focus on at Bentley. It is open and extensible, first of all. BEAS by itself, we maintain it in a project in GitHub. And you can contribute, and contributions from the public are welcome. It is extensible in the sense that anyone can create a busy schema as long as you follow the basic rules and patterns. It is meant to be multidisciplinary. We believe its rules and patterns are useful across all life cycle phases of an infrastructure asset. It was designed for the two workflows that I mentioned earlier, the synchronization workflow, where the single source of truth is outside of the iModel, and you're really bringing the data into this format, as well as authoring, in which you're using this ecosystem to create the data. The semantics that it captures are captured in an object-oriented fashion. It's what we mentioned earlier throughout these presentations: inheritance, relationships, property sets that we call aspects. We support polymorphism. We have a similar concept of mixins, similar concept to interfaces in some languages. And lastly, the term that I used a few slides ago, modeling perspectives. B supports multiple modeling perspectives captured in the same iModel. So let's dive into some of the details here. BEAS has a number of core concepts, and I picked 4 of them to talk about at this presentation. I'm going to discuss the concept of an element, elements contained within models, a model following a particular modeling perspective, and all that organized in one hierarchy that we call the subject hierarchy. So just let's keep those 4 building blocks in mind. So I'm going to describe those building blocks in terms of a more concrete example, an example of a piping system, let's say in a plant. And we have 3 teams collaborating, one of them focusing on the functional point of view, where they are describing how the different pipe components, valves and pumps are connected with each other, certainly producing the associated schematics. Another team, it could be even a totally different organization, doing the 3D modeling. In Advently, we call it a physical modeling, of the plant. Again, the use case there is probably visualization, class detection, quantity takeoffs are examples of goals there. And another team doing some structural analysis of those pipes, running simulations and options in order to find the best way to structurally support those components. Just I want to describe the 4 building blocks in light of this kind of more concrete example. All right, so let's just grab 2 of those 4 building blocks, the concept of elements in light of modeling perspectives. I think this was going to be easier with an animation, but let me give that a try. So we have multiple schemas in this, and in order to model a functional pipe, we could introduce a schema just targeting that particular modeling perspective, the functional, which is the green on the left, and define a class on that schema that fulfills the needs of that team. That team introduces a number of functional properties on that class, and we call it the functional pipe. And we instantiate that class, and the rounded box that you see there in the middle in green represents an instance of that class. It has a name, P001, and that is basically the granularity that they need that data to be described at. The other team focusing on the physical modeling, they follow the same thing. They create a schema focusing on the physical modeling perspective with a notion, a class called physical pipe, with the list of properties that they need for that use case. And in this example, there are 3 instances in dark blue that represent actual elements representing the physical pipes at the granularity that is needed. Just realized that I forgot to mention what an element is. In BIS, an element is the smallest identifiable concept that is offered. It has a few ways of identifying it. It has an internal identifier in the database. It has a global UUID as well, so for federation purposes. And for those components that in some industries it is important that they carry a code, a piece of a string that has a lot of business meaning for in the industry or for a given customer. So we also have that support. Elements can be coded, can have a federation GUID, and also have an internal ID. With that said, I was describing that we have three physical instances, three elements in blue, and one functional element in green on the left. This offers a number of relationships in order they are semantically rich. And in this particular example, I'm going to talk about one of them. It's called the physical element fields function. And that's how we can associate instances on the physical side with the functional. And these relationships are many-to-many. We understand that the granularity of the modeling done at each perspective may be different, and therefore these relationships have to be many-to-many. We don't assume that it is a one. Analytical element simulates, so that's the semantics, simulates spatial elements is what we call it. I purposely put the physical modeling perspective in the center. We consider the physical perspective as the backbone of the others, and that's how they relate with each other. The other concept that is mentioned in this slide are the element aspects. We support a similar concept of the property sets in IFC. Similar, not quite the same, in which you can attach sets of properties to these elements. So these properties become optional, but you could do it across any of these modeling perspectives. So you have, first, to summarize, you have first-class properties that you can define on a class focusing on a particular modeling perspective, or you can have properties that are attachable at a later point. So I mentioned elements, I mentioned modeling perspectives. Now let's talk about models. And I'm probably overusing the word model here, but fortunately that's what we went with. So model is a container of elements. In BIS, every element has to live in a model, in one model. The usefulness of models, I'm going to go into that in a second. But I just wanted to prepare you mentally. So in the slide, I'm showing four elements on the left contained within two models. And the models contain elements of the same modeling perspective. So that's what we expect here. At the center, we have two models containing 5 elements on the physical modeling perspective. And on the right, we just have, in this example, one model containing 5 analytical instances. Notice that the relationships across these modeling perspectives and models are still there. They are not really affected by this concept of models at all. But now let's put everything together into one of the hierarchies that we support. BIS has received quite a few inspirations from IFC. We have the same pattern that has been mentioned today multiple times, multiple taxonomies going on here, multiple hierarchies. Just to briefly mention, we have a hierarchy focused on the spatial decomposition of facilities. You know, that certainly matches the spatial structure hierarchy in IFC. We have hierarchies of systems, in these hierarchies of networks. Those are hierarchies built for a particular purpose, and they are introduced for the whole ecosystem of the schemas in these. The hierarchy on the screen is one specific hierarchy that is important because it drives the organization of elements and models in an iModel. So what is at the top of this hierarchy? We have some spatial elements called subjects, whose job in the BIS ecosystem is about describing what the AI model is about. And at the top of that subject hierarchy, the very top, we have a subject that we call the root subject. And this, in this example, is telling us this AI model is about plant ABC. Then you can have as many levels as you need in order to decompose that subject matter of the AI model into more granular areas. But this is all driven by a user. So this hierarchy is meant at the top of the hierarchy to be driven by the organization that fits a particular user's needs. So all of these subjects, their names are in the user's language. This is it is capturing some information that really software cannot understand by itself. You need a human to tell you which branch to follow. However, at some point of the hierarchy, we need to jump into the concepts that I described earlier, modeling perspectives. So for a particular subject in this hierarchy, I'm showing here the plant process, is where we have a layer of another spatial elements. We call them information partitions, advertising being the entry point of these modeling perspectives. So these are the elements that once software scanning this hierarchy, once they are found, is where the discoverability happens. The element at the center, called physical partition, it's advertising what follows is a model, a container, that has the elements that are describing a particular subject. In this case, the physical pipes. Same with the functional partition, being the entry point to a model, capturing the physical elements for the functional modeling perspective of that subject, and on the structural analysis as well. And it is the concept of those models in light of this hierarchy that allows us to enable multi-user workflows and data ownership. Each model can be seen as a boundary that we can enable locking. So a given team, a user, or even organization can lock each one of these models and write to them individually or have granular control over this data via these boundaries. Let's see. All right. I think I've mentioned the subject hierarchy, the elements, the concept of a model. Let me move forward of how we organize schemas in BIS. We follow a similar organization as when you develop software in a tier manner, in which probably the lower tier is more generic and provides the framework for tiers above. That's what we did with BIS. We have 5 layers in which we organize our schemas. At the very core, at the very bottom, it's the core layer, a handful of schemas that define the most basic and fundamental concepts and rules that apply to the whole ecosystem. The 4 concepts that I mentioned earlier are defined at that level. Then we have the next layer, we call it the common layer, and another set of schemas that introduce abstract concepts and patterns used by multiple disciplines. And examples of these schemas are linear referencing, grids, classification systems, profiles, abstract concepts, but they introduce rules and patterns for those topics. Then you have the discipline physical layer, capturing schemas that focus on the physical modeling perspective and try to standardize, provide base classes for more discipline-specific assets. So this is where we find schemas that describe, for architectural, structural, road and rail purposes under the physical modeling perspective. On top of that, we have other schemas at the discipline other layer that they focus on some other modeling perspective. Structural analysis is an example of that. road and rail networks, another example. And at the top of these tiers, we have the layer that captures schemas that are really not meant to be referenced by any other schema. Schemas that are created by applications, schemas that are created by end users, or dynamic. The word dynamic here in the slide means schemas that are created at runtime as well by the pieces of technology that I mentioned at the beginning, iModel connectors, that bring data from an external data source into an iModel. They typically create these schemas at runtime. So the extensibility part of this is built by schemas created at that layer. I should note that the schemas at the first 4 layers are the ones that aim at some basic standardization. These are the ones that we evolved in GitHub out in the community. The schemas at the application dynamic layer, certainly those are not aiming for standardization, they aim for extensibility. A quick sample of how you can query data from this. We have a language called EasySQL. It is an SQL-like language that you can use to retrieve, well, actually do all the CRUD operations against an iModel, but this is via this. And that's because the from clauses of that you see on the screen here, they are not really physical tables. They are concepts or classes introduced in some particular schema in the Biz ecosystem. Some of these examples, the first one is quickly querying for all the labels from a class called pipe in a schema called piping physical. The second example is describing polymorphism. We can assume some user-defined schema called my piping schema, where 2 classes, my physical pipe 1 and 2, were created. And those probably are subclassing the concept of a pipe in a shared schema. Let's assume that a schema is piping physical. So this query is basically retrieving labels from 2 particular end user created schemas, but making sure that they are really pipes. They share the same ancestor. The third example, using a group by in order to reduce the number of instances or elements, in this case pipes. If you see the from clause, and group by nominal diameter, that's a property. And finally, showing a little bit of the join support. This is joining the concept of pipe in a functional schema by using a relationship. So relationships are also treated as classes, and they support inheritance and all that. In this case, the relationship is the one that I mentioned a few slides ago, physical element fulfills function. And that particular query is just looking for, it's going to give you the functional pipes that don't have any associated physical elements in the iModel. That's why in the where clause is doing some is null check. Yeah, my last slide. So just to close, I'm trying here to describe the bigger picture. We have a platform as a service offering from Bentley called iTwin platform. And once data is associated to an iTwin or uploaded, synchronized to an iModel, you can do a lot of things with it. All of these circles represents cloud services that today they exist as part of this iTwin platform. They were all written by using the open source library that I mentioned earlier, iTwin.js. I should just mention a couple of services in particular. The entity registry is one that acts as an index. We acknowledge that a particular entity of business significance may show up in multiple iModels or multiple data sources associated with an iTwin, and therefore we need to tie them together, and that's a service that is in charge with that. Certainly we have several services for data cleanup, validation, associating sensor data with a sensor device that you may be modeling in an iModel. And you can leverage all this data that you have in an iTwin with services downstream that will give you carbon calculations, reporting services, or exports to IFC as one example of the export formats that we support. Well, I hope this has been useful. This is what I had prepared for you guys today. Thank you very much.
Thank you, Diego.
We have just a few minutes left. Any questions from the room or online to the room? Or to Diego?
There's nothing online, right?
The one thing I did make note of is in previous discussions when we brought up this ECS model, Devon has pointed out this concept has had a few names, and Vixens was one of them. You mentioned this in your in passing. Do you mind sort of making the link for the room on that? Discuss that.
Sorry, what exactly?
Vixens, you said?
So what are they? You need to
Just make the connection of explain a little bit. Yeah.
Well, the easiest way to describe that is if you have done any programming in C# or Java, you have the concept of interfaces. Those are typically languages, or they don't support multiple inheritance the way C++ do. So in C# and Java, you have single inheritance, but you support polymorphism via interfaces. And that's the way we do it in Biz. We support single inheritance as far as classes. And these are like interfaces that they carry either properties that you want to standardize or implement on particular classes, or they can be used as endpoints for relationships. So you can define a relationship that says, any object, any class that implements a particular mixin can be the source or the target, one of the endpoints of the relationship. So that's the concept that we use in this.
Anyone in the room? Online? Or wait. There's my questions online. Yeah. So okay. Well, so we're at the almost the top of the hour. We have a break for a half an hour. So anybody that's Greg or Devon, if you're able to stick around, we'll come back. First thing we'll do is have Leif present, and then the last topic we have for the day is just sort of a little bit more. Okay, how do we move forward with this concept in the building smart world? So that's it for now. I thank everyone very much for taking part and presenting. I think it's a pretty nice session to see these diverse approaches to this topic. I appreciate it quite a bit. Thank you.